I know it's only one letter less, but we as mathematicians want to be very concise. We don't need 3 A's, we only need 2 A's. So you write angle, angle, similarity. It's because third angle theorem would get us the third angle. This shows triangles are similar. This is state test, this is the one they love the most. So angle, angle to show 2 triangles are similar. That's the best one. 2 angles, it's pretty simple, just 2 angles. That's good. Now there are 2 more. That's it. I'm going to come back with more later on. There's only 2 more after this. Side, side, side similarity. Notice on these you must write this. There's a difference. This is for congruence. This is for similarity. You must write this.
Along the sides of like a fraction that matches.
That's it. So if you know nothing about the angles, let's say I knew, let me just make up some numbers, 4 and 8, 5 and 10. All of these ratios, I know nothing about the angles, but all the ratios there are 1/2. So you have all the ratios the same, and the triangles are similar. And the word for, oh sorry, it's filled in for you. The word for all ratios the same is proportional. It's already filled in. So I put down here, yeah, if you have, this is all the ratios the same, then the triangles are similar. So good job, yeah, thank you for saying that. And then you could probably guess at the last one, right? SAS similarity. So you need like an angle, let's see that. So like you need a pair of angles congruent, and then the ratios of these sides to be the same. So again, I'll just choose some numbers. Maybe it's this. Again, the ratio there is 1/2, and the included angle is congruent. So that would be SAS similarity. Side angle, side similarity. So there are 3 ways to show triangles are similar. Again, I've started the angle, angle one. It's the simplest one, and it's the one that they like the most. There's 3 ways to show triangles are similar. So we're going to do, this is similar to like what we did with these days, SAS and angle, side angle. Let me give you a few diagrams and let's see if we know the triangles are similar. Any initial thoughts, anything to add? So very, very related to what we've been doing. All right, I'm going to pick and choose a few of these. I'm not going to do all of them, but let's try a couple here. Are the triangles similar? And we'll state one of those 3, or we could say no. We could say no, they're not. All right, so let's actually start over here with the last one. I have a pair of 45-degree angles, right? And their bow tie, right? So I can mark vertical angles. So that's all I can mark. You have 2 congruent angles. They're similar. AA similar. And again, the simplest one is get 2 angles congruent. Let's actually do the middle one. I have 68, and each of these is isosceles, right? Those are congruent. So these are both 68. Isosceles here. Well. Well, that's what we're trying to figure out.
I don't.
So this is 62. Now if I subtract from 180, that would leave me 118. And when I divide that by 2, I'll get 59 for each of these. 120, 136. If I wanted to, I could solve this one to 44. So here we have 2, we have a pair of isosceles triangles. Do you think those are similar? No. Again, what you can do is always try and find as many, so I'm just going to put not similar or not enough information. You can try and solve for the angles, but again, look at these. Angle, angle, SAS, and SAS, SSS. You need an angle to be congruent. There are none of them between the triangles. Between the triangles. Or you need all 3 sides. We only know something about 2 sides. We don't even know something about the 3rd side. All right, I'm going to skip the other one. Let's do a couple more on the next page. Any thoughts on those? Okay, I'll probably do the first and third one here. So, same question. Are the triangles similar? Let's look at these. Well, we have 3 sides. Know nothing about the angles. So hopefully SSS similarity will work. Well, let's check the ratios. Now you can already see that the triangles aren't in the same orientation, right? They're like flipped or rotated. Here's what I know. I'm going to start with the 6 here. I'm going to check ratios. The 6, the smallest side here, in order for this one to even be, to possibly match up, it must go with the smallest side over here. Okay? And so I'll try it now. The numbers might not work on the others, but it must go with the smallest side there. It has to go with the 9. Let me do the others and we'll reduce. So if I go to the medium length side, 8, that has to go with the middle side there, which is 12. And then 10 must go with 15. Are those the same ratio? Same number? Yeah, and so they are. You either put them in your calculator, it would be 0.6 repeating, or you could reduce it as a fraction to be 2/3 for all 3. So this one is, yes, SSS, similarity. But I put it right here. Again, you have to match up on these. The smallest sides, the middle sides are the longest. And you know, lots of times they have these marks, right? Like usually they tell us which. Usually they have these marks that tell us which sides will go where. If they don't, then match up the smallest, middle, and largest. Okay, let's do the last one here. I like this one. Are the two, let's see, it's still the same. Are the triangles similar? Do you see that there are 2 triangles here? There's that one, and then there's the bigger one. There's this one. They're overlapping. If you'd like, you can draw them so they're not overlapping. For example, here's a KLP. And then I'll just leave KMN as the big one. So let's see, are the triangles similar? Well, let's compare the sides that I know. I only know this triangle, the 8 and 12. So let me do 8 here will correspond within the red triangle 10. Yeah, 8 and 2. Let's check this side, 12, and that must go with this one, 12 and 3, 15. Are those the same? They are. They're 0.8. Each of them is 0.8. If you reduced them, they would both be 0.8 or 4/5. So what we have is we have 2 sides that have the same ratio. That's good. But we need to see if that's. I don't know the third side, so I need to hope for an angle. Yes.
Could you use the angle for angle K?
Exactly. Yes. Thank you. Angle K is a shared angle, so it's got to be the same, right? Just like a shared side, it's got to be the same line. Shared angle. Well, that's what people. Shared angle in both triangles, and so it's congruent. So we do have, and it's included. So this one is yes by SAS similarity. Do you know what reason this would be in a proof if we wrote this angle is congruent to itself? It's reflexive. Just like we normally write here, like AB congruent to AB, we'd write angle LKP congruent to angle LKP. Reflexive. Because it's the same, it's like A equals A. Okay, good job with that. I'd like to do, yep, there are proofs with these, so a couple proofs in this. I'll do a couple proofs. Any thoughts on those that we did? Yeah, I have it.
Is there ever a situation where you would switch it like angle LKP congruent to PKL?
That's a good question. Not that I can think of. However, what's interesting about this one, so to answer your question, I don't think so, though. To answer this question, something else though that you could say angle LKP congruent to angle MKN, and it's still reflexive because that's the same angle still. They named it. I named it differently. In the blue triangle, I said LKP. Big triangle, MKN. It's the same angle.
You could name the same angle
In different ways, yeah. I don't know why you really want to in general. Like I wouldn't know. I would say LKP. But you could. Good question. This one I'm actually going to skip. It's a proportion one similar to yesterday, and actually it leads into what we got to do next week when there's parallel lines and triangles. So I'd like to do these two proofs, bottom of 5 on the next page. Okay, and guys, I think you'll if you like SAS and angle side angle, these ones from congruent triangles, well, it's not much new. It's the same things. So if you like that, then you're probably going to like these as well. So we have this triangle given, and AC is parallel to MP. And we're going to show the triangles are similar. So I wrote in the given. Step 2, there's a couple options. What would you like me to do? This, again, normal triangle proof. What would you do here? Maybe vertical angles, or you could use this. Either one. You said this, that's fine. I'll say angle ABC congruent to ABC. Angle PBM. Vertical angles theorem. And by the way, we don't have any sides given, no ratios, so we're probably just going for AA. That's as simple as 1, 2. Just get 2 angles congruent. What's the other thing we're going to do? Since there's parallel lines. Good. Alternate interior. Thank you. So you could. I'm just going to choose C and M. You could choose C and M or A and P. It's up to you. Angle C congruent to angle M. Actually, this one could have been 3 steps if you wanted to just do both sets of alternate interior in step 2. And then the triangles would be similar. Let's see. Alternate interior angles theorem. And that's it. We got 2 angles congruent, so the triangles are similar. Triangle. One second. Triangle ABC similar to triangle PBM. Angle, similar. Yeah, Caleb.
How do you know if you need to label it like angle C or angle ACB?
If the vertex is alone here and there's no other segments with it besides these 2, you could call it C. Or you could say ACB if you want.
Well, could you say
But-
angle B?
No, because there's not just like angle B could be that, but since there's other segments coming from that vertex, we don't know what angle B could be. This one or that one or that one or that one. So we can't name it because we don't know which one of those 4 angle B would be. Right, not too bad here, right? Really the only new thing is this: 2 angles congruent. They're similar but angle. I want to look at one more proof on the next page. So flip it over, next page, one more proof. This is a good one. And again, we're just going to show the triangles are similar here. It is the big triangle, LMO, and then the smaller triangle inside, P and O. Write down, we're provided, besides the diagram, we're provided that LM is perpendicular to MO and PN is perpendicular to MO. And so I'm going to just directly go for my givens, these, and state what those do, right? If LM is perpendicular to MO, then that would be a right angle. Right, perpendicular. And if PN is perpendicular to MO, then both of these will be a right angle, but the only one I need is the one in my small triangle. So I can put both. But. So I'm going to write that those are right. This is a perpendicular, 2 steps here in the process. Angle P and O and angle right angles. And then we'll say they're congruent. So step 2, let's see, they're right angles. This is just what perpendicular means. Intersects to form right angles. So definition of perpendicular. And then we can say that they are congruent. Angle P and O congruent to angle L and O. All right angles are congruent. So we use perpendicular to get a pair of angles in the triangles congruent. We have nothing about the ratio of the sides. But we're going to use, this is what you were saying earlier, I think, right? We're going to use the shared angle. So I wanted you to see how we write this, yeah. So in the small triangle, it's that angle, and in the big triangle, it's the same angle. So they have to have the same measurement. If we didn't have this thing here, I don't even know. If that wasn't there, you could just say angle O. But because it is there, I'm going to name it with 3 points. That's like what you were saying. Since there's another segment coming from here, we can't name it angle O. So let's name it PON. How many do you think?
I don't know, but I'm running out of space.
Angle PON congruent to angle PON. In the small triangle PON and the big triangle PON. The little triangle, it's this angle.
It's the LMO. LM.
You could say LOM congruent to LOM. There's different ways to name it. You could say.
Are there more steps?
There'll be one more step. That is exactly the same thing. Angle PON congruent to angle PON, so it's reflexive. First time I think we've seen it for angles. All right, and therefore, in the small triangle we have those 2 angles, and in the big triangle we have right angles and the shared angle. So the triangles are similar, right angle. So yes, 5 steps. What is it? Triangle LMO similar to triangle P and O.
I don't understand why you have to do PON and PON.
It's like when they have a shared side, you have to say AB congruent to AB. So same thing here. They have a shared angle, so we name the angle congruent to itself.
Oh, do you really know how to use the?
Probably not, because they can't be. You couldn't have these. If they're like this, they're going to be congruent. You couldn't. Although you could have one bigger than the other, but then it wouldn't be a shared side, and they wouldn't have a shared angle. So probably not. Probably not. Any thoughts on that proof? Well, it was actually the only new thing again was angle. Perpendicular was reviewed. Oh, and the congruent for reflexive. I need to finish up with one last example about indirect measurement, and then we'll be done. So, middle of the page there. This kind of flips gears. Well, no, it's actually just it's an application of similarity. So, here's what I want to say. You can indirectly find lengths using the properties of similar triangles. What we're doing. This is called indirect measurement. For example, if you want to find, I know you have phones these days, but suppose you want to find the height of the Eiffel Tower. Here's what Nina did. Here's what you could do. She used a model. So I'll put the model here. She used a model of the Eiffel Tower. That's my Eiffel Tower. I don't know how to draw it. So she used a model that's 1.2 meters tall. And she measured its shadow at 2 p.m. So here's the sun over here. So there's the model. Here's the ground. the length of the shadow was 0.9. Right? The sun's shining down, it made a shadow of 0.9 meters. And her model was 1.2 meters tall. Then she measured the Eiffel Tower shadow. So here's the actual. Here's the actual Eiffel Tower. By the way, draw this picture. Help to see it here. The actual Eiffel Tower, and measured its shadow. I should have that dotted. And its shadow was 240 meters at the same time. That's important. So you can see how I've made triangles out of it. Here's why we can do similar triangles. Since we assume they're both straight up and down, right? The Eiffel Tower and the model. There's a right angle. And because at the same time of day, this angle will be the same. Right? The angle from the sun is the same. You can't do it at like noon and then 5 p.m. It'd be different. Aren't these triangles similar? Same reason as we've been doing a lot of angle. They're similar. So since they're similar, we can do stuff that we've been doing mainly from yesterday. We can do a ratio or proportion. So let me call this one x, the actual height. We can do a proportion such as x over 1.2 equals 240 over 0.9. You could have started in the small one, you could start in the big one, but that would be the proportion and we cross multiply. So when we cross multiply here, it's 0.9x. 1.2 times 240, you get 288. And then we divide by 0.9. So what you get is 320. The other thing I want to say about this one is you could have also drawn these as overlapping triangles. The model here, and the sun's up here. Okay, you still get the same thing and the same reason. I just decided to separate them. So, because they're similar by angle, you can set up a proportion and so on. Okay, I'm going to